Good afternoon. We will discuss today about the rejection of data. In fact, this is in continuation of my last class where we have discussed about the method, that is the Chabinet criterion, in which is used to reject data, that is experimental data. And now what we will do, we will take up an example, and then considering that example we will see that if we use the Chabinet criterion, rather the steps which we have outlined in the last lecture, we will try to follow those steps to reject a particular data. So, just we will take an example, say example we are considering, that is the rejection of data using the method, and that is known as Chabinet criterion. So, example, that means we will be using Chabinet criterion to reject experimental data. Now, if we have set of experimental data, suppose I am writing, suppose we have 10 measurements. That is, say if we just list down 46, 48, 44, 38, 45, 47, 58, 44, 45 and 43. So, if we just look at this set of data, we can really find that the data point 58 and 38, these two data points are not in the order in the sense, if we look at these 10 different data points, we find that 58 and 38, these two data points are not the maybe correct, because remaining other 8 data, I mean 46, 48, 44, 45, 47 and 45, 44, 43, these remaining 8 data, they are having almost similar magnitude, but 38 and 58, these two data are not falling in this range. So, if we now consider the steps, that is, we can see from this data set that 58 should be rejected and 38 also should be rejected from this set of data. Now, we will see if we use Chabinet criterion to eliminate data, that is 38 and 58, then we will use the steps that we have understood in the last lecture. So, the first step is mean. So, if we now try to calculate step 1, right. So, the mean is 45.8 and the standard deviation is 5.1. So, the standard deviation is 5.1 and mean is 45.8. So, we have 10 data points and mean and standard deviation we have calculated, right. So, that is step 1 and step 2. If we follow step 1 and step 2, then we can calculate this. Now, what we can see, the measurement 58 is the furthest from the mean. So, the measurement 58 is the furthest from the mean at 2.4 standard deviation from the mean. So, from the mean. Now the probability getting a measurement 2.4 sigma or larger is 0.016. And right. So, if I now go to the next slide. So, the probability. So, we can see that if we have calculated standard deviation and mean, and the measurement 58 is the furthest from the mean, and at a standard deviation 2.4, at 2.4 standard deviation from the mean, that is what we have calculated. Now, the probability of getting a measurement 2.4 sigma or larger is 0.016. So, that is what we have calculated probability. Now, if we here if we follow the steps, then P is 0.016. Following the Chauvinet's criterion, we have calculated mean and standard deviation, we have calculated error, that is Ti for each data, then we can find 58 is the farthest. So, that is Ts is maximum. So, Ts, that is called Ti, the number. If I calculate now error for each measurement, and then we will find 58 is the furthest and error is maximum, and if we call it Ts, then 58 can, I mean we can expect that 58 should be rejected. Now, this 58 is the furthest from the mean at standard deviation, at 2.4 standard deviation from the mean, and the probability of getting 2.4 sigma is 0.016. Using that probability density function we can calculate. If P is 0.016 and N is 10, that is 10 data points are there. So, now small n, that will be 0.16, small n, that is capital N into P, that is 0.16. So, if we go to the next slide, then we can write that we would expect .16 measurement like this, and this small n is less than half. So, we reject the measurement of right. So, we can reject 58. If we reject 58, then now if we go back to the previous slide. So, if we reject 58, then we will have 9 other measurements, and again we have to calculate the new standard deviation. So, if we calculate the new mean, so after rejecting (58), new mean is 44.4, that is very simple. If we calculate with a standard deviation of 2.9, right. So, if we follow the similar steps, then expected number of measurement as bad or worse than 38 is 0.244, and so we could reject that too. So, I am writing this, that means after rejecting 58, to reject 58 we have followed the steps which are rather using Chavinet's criterion, and we have seen that 58 can be rejected. After rejecting 58 we have calculated new mean, new standard deviation, and if we follow the steps that we have outlined in the last lecture, and we will see that 38 also can be rejected. So, the expected number of measurements as bad or worse than 38 is 0.244, which is also less than half, and we could reject that too. So, this is what is called Chavinet's criterion for the rejecting data. So, this is not very difficult, we can reject data using this method. And so, this example I have taken only considering a few points, but in real experiments if we record, if we collect data, then we will have 50 or 100 data points. From there obviously a few points will be there which we can reject, and we can reject data using this method. So, next we will be discussing about the error propagation. What is error propagation and why do we need to study this aspect is also rather we should know about this. And there are a few cases, in fact in many instances we would like to use measured data to calculate or to predict something else. Say for example, we would like to calculate velocity using the measured value of pressure. So, if we measure the pressure using manometer, and by measuring the pressure we can calculate, we can predict the flow velocity. So, if we now take this example, say so what I have written is that in many instances we want to use measured data to compute something else. So, if we now take the example that velocity from dynamic pressure. Velocity from dynamic pressure, this is the example, that means the pressure, the dynamic pressure measured with a pitot tube can be used to compute flow velocity, right. So, if we say velocity is y, then y is equal to square root of dynamic pressure, say x, where x is the dynamic pressure and y is computed velocity. Now, if the pressure which is measured using pitot tube or using manometer is found, say if I go to the next slide, say what here I am writing x is 5.0 plus minus u. That means the pressure which is measured using manometer is found to be 5.0 plus minus u, where u is the reported uncertainty of the manometer, where u is the reported uncertainty for the manometer. So, that is what I was talking about in the last class, that any system, instrument or device which is produced in a manufacturing manufacturing unit should be certified with the uncertainty. That means, that is what I took an example, that if a product production unit is manufacturing gas tank, then the internal gas pressure that will be that should be considered the design value of internal gas pressure for which cylinder rather gas tank can withstand without any mechanical failure should be certified. That means, it is not the case that the gas tank will be always safe at the design value, rather we will have plus minus range of operation. That means, if the design value is x, then x plus minus should be the range for which the gas tank will be safe for the operation. Similarly, when we are using manometer in for the measurement of the pressure, then the reading which you are getting from the manometer should be something plus minus uncertainty range. Now, if the measurement is measurement x for this particular case, that is the pressure that we are measuring using manometer is 5.0 plus minus u, where u is the reported uncertainty of the manometer, then from the statistics I am writing next slide, that is from the statistics we can show that the mean value of the velocity, from the statistics we can show that the mean value of velocity will be given by y that equal to minus infinity to infinity root of x this probability density function dx, where Px is the probability density function for the measurement of x, right, and the standard deviation. So, this is I am not going to discuss that part. We can show from the statistics that the mean value of velocity will be given by this expression, and the standard deviation that y prime is minus infinity to infinity root of x minus mean square p x dx. So, this is the standard deviation, right. So, from this we can conclude one important thing, that in general the average of the computed velocities will not be equal to the value of the velocity computed with the average dynamic pressure, right. That means, the average of the computed velocity will not be equal to the value of velocity computed with the average dynamic pressure. So, this is in general. So, this another important thing, if we now go back to the previous slide, then this Px, probability density function, is, if we need to calculate the standard deviation and mean value of the velocity, then we have to know the probability density function explicitly, and these integrals could be very difficult to evaluate. So, this is the case. Now, the x, what I mean, we have written that is 5.0 plus minus u, right. So, that is what we have written in the last slide. Now, if we assume that u is small number compared to 5, the mean value. So, if the uncertainty is very small, and then we also can assume the probability density function Px is normal probability distribution, is well approximated by the normal probability distribution. So, if we go to the previous slide, what I said, that if we need to calculate the velocity, average velocity, the mean value of the velocity, then we have to know explicitly the probability density function, and this integral could be very difficult to evaluate. And for that, we are considering that we are assuming that u is very small, that is uncertainty is very small, and the probability density, that Px is well approximated by the normal probability distribution. In that case, if we try to plot of the variation of y with x, right. So, if we try to plot it, then this is x, this is 0, 1, 2, 3, 4, 5, 6, and we will get now so that is, this is y equal to root x, and this is straight line approximation at x equal to 5. So, we can at x equal to 5 we can assume the straight line approximation. So, what we can see is that means we can see y equal to root x and the approximation rather straight line approximation at x equal to 5, that is a first order Taylor series expansion. So, y is equal to root x, and if we consider straight line approximation, then that is at x equal to 5, that is a first order Taylor series approximation at x equal to 5. What we can see from this figure is that very important that as long as we remain close to 5, that is 4 to 6. So, this is 1, 2, 3, 4, 5, then this is 6. So, as long as we remain close to 5, 4 to 6, the difference between straight line and curve is very small. And if we consider this, so as long as we remain close to 5, then difference between straight line and curve is very small, and thus it would appear that we would be able to use straight line approximation. For the function. So, we would be able to use straight line approximation for the function. Now, this is what we have discussed. Now, if we approximate by the straight line, then the result of this approximation is that the mean value of the velocity is equal to the velocity calculated with the mean dynamic pressure. With the mean dynamic pressure. Right. That means, from this exercise we would like to draw an important conclusion is that the mean of a function calculated with the measured variable is equal to the function calculated with the mean value of measured variable provided uncertainty is very small. So, that is why I was doing this exercise, that from this typical example we have been able to show that the mean of a function calculated with the measured variable is equal to the function calculated with the mean value of measured variable, provided the interval of uncertainty is small, right. So, this is an important conclusion which we should know, at least who are doing experiments in the area of fluid dynamics. So, this is what we have discussed, and also we would like to see that error in velocity would be proportional to the error in pressure. That is what we can see. That means E y, that will be f dot x E x, that is 1 upon 2 root x E x, where E x and E y are the error in x and y respectively. And standard deviation of y, that is sigma y, will be equal to f dash x into sigma y square, that is 1 upon 2 x into standard deviation x, that is sigma x. So, standard deviation of y can be also related to this standard deviation of x with this relationship. Now, this general method which we have discussed can be used to estimate the error in the computed value of a function of a single variable. So, till now we have discussed that, taking an example, we have discussed that the error, this method can be used to calculate, to estimate the error in the computed value of a function of a single variable. That means computed value is y, which is function of single variable, that is only x, and we can calculate E y error. So, that is the important. So, we can calculate. So, I am writing this general method can be used to estimate the error in the computed value of a function of a single variable. So, till now we have discussed a case where we have calculated y, which is a function of a single variable, but if we now have, we will see that if we have function of two variables, function of two variables, say we have a function z which is f x y with similar notation as above. So, that is we have a function z which is the function of two variables, that is f x and y with similar notation that we have discussed till now. So, following the same procedure we can, following the same procedure we assume that we can use a linear approximation to the function about x comma y, that and given by E z, that is del f del x x y E x plus del f del y x y E y. And what we do, we then square an average to give sigma z square equal to del f del x x y square sigma x square plus 2 del f del x x y del f del y x y E x E y plus del f del y x y square sigma y square. So, where we can see, if we now go to the next slide, just I am doing this mathematical analysis. So, following the same procedure, we assume we can use a linear approximation to the function x and y, and then we can calculate error in z, and we can then square an average to obtain the sigma z square, that is the standard deviation. And then what we can see from this equation is that we have the average E x E y that equal to 0, where we have the average, E x E y 0, as we can assume that the errors in x and y are statistically independent. Thus, sigma z that we can write del f del x sigma x square plus del f sigma y square, right. So, this is we have calculated. If we go back to the previous slide, that means we have considered today one case where the function is a single variable function. We have discussed the steps in detail and we have calculated the error and the standard deviation. If the function, if we consider a function of two variables, then following the same procedure we assume that we can use linear approximation to the function, and we have calculated the error, and just we then square an average to obtain the standard deviation. But here that we have the average Ex Ey that equal to 0, and we can assume that the error in x and y are statistically independent, and we have calculated. Now, if we consider function of several variables, general that means if now writing, so that means if we now consider function of several variables, right. So, we need to know the error propagation, that is what we have taken on one example, but if the function is having several variables, then the general procedure is identical for functions of two variables. And the result is that the error is the result is that the error is given by the general formula sigma f, that will be, so I am writing in the next, okay, I am writing here, given by sigma f is equal to under root I equal to 1 to n del f del x I x bar sigma x I square, where x I is the ith argument of f a function of n arguments, right. So, this is the case. Now, so this is the case if we consider the several variables. So, what we have discussed is that if we have the single variable function, then we have discussed about the error propagation, what do mean by that, and we need to know that, and finally we have come up with an important conclusion that the mean of a function calculated with the measured variable is equal to the function calculated with the mean value of measured variable, provided the interval of uncertainty is very small. That is what we have seen today. And finally, we will work out one example that which is, we have discussed about the error. Today we have discussed about the different types of error, and now we have seen that the errors, measurement errors can be classified into three different categories, that is the blunders, fixed error and random error. Random error cannot be eliminated, can never be eliminated rather, and blunders can be eliminated, I mean if we are careful in measuring data and when we are using any instrument to measure data. And fixed error, the fixed error can be we have given one example, and from there we have seen that the fixed error can be eliminated provided if we consider the correction factor. So, now what we will do, we will work out one example which is related to the error. Now, fixed error I can say. So, we have seen that the random error cannot be eliminated, blunders can be eliminated if we carefully use instrument or device in measuring data, while fixed error can be eliminated, I mean we can eliminate rather if we consider the correction factor. So, as I said that the errors cannot be completely eliminated, but it can be minimized. So, if we are careful in measuring when we are measuring any variable using any particular instrument, then we can reduce the probability of the error. Now, I am considering one example of fixed error. So, example that a 12-inch steel scale is graduated in an increment of 0.01 inch and accurate when used at ambient temperature of 60 degree Fahrenheit. Calculate the error in an 11-inch measurement when ambient temperature is 100 degree Fahrenheit. Second question, should the person using the scale be concerned about the error? And why? So, this is the example. We have to calculate that a 12-inch steel scale, that is a metal scale, is graduated in an increment of 0.011 inch and accurate when used at ambient temperature of 60 degree Fahrenheit. We need to calculate the error that we will definitely get with an or in an 11-inch measurement when ambient temperature is 100 degree Fahrenheit. Second question is, the person who is using who will be using this scale be concerned, the person who is using or who will be using this scale should be concerned about the error. If yes, then why? So, now one hint is given that the linear coefficient of thermal expansion of steel, that alpha is 7 into 10 power minus 6 degree Fahrenheit inverse. So, this is given. So, this is given. So, if we work out this problem, then we can write that we have studied from our 10+2 physics that LT will be equal to L naught into 1 plus alpha into T minus T naught. So, this is what we have studied in our 10+2 level physics. So, the with a change in temperature, we have the linear coefficient of thermal expansion, then what will be the change in length with a change in temperature. So, this LT is the length at temperature T degree Fahrenheit, L naught is the length at temperature 60 degree Fahrenheit, right. So, our objective will be to calculate at 100 degrees Fahrenheit temperature, that is L. So, we can write that T naught degree Fahrenheit. So, this is T naught degree Fahrenheit. So, L 60 into 1 plus 7 into 10 power minus 6 into 100 minus 60. So, that is what we know, and this is very simple, very straightforward class 8 level algebra. Now, we can calculate L 100 minus L 60, that is L 60 into 7 into 10 power minus 6 into 40. So, this is the error in indicated length. So, this quantity is error in length, and that will be equal to that 11 into 7 into 10 power minus 6 into 40. So, if we now go back to the previous slide where we have written, that means if you would like to calculate, if you would like to measure 11 inch using the same scale, we will get error, that is 3.08 into 10 power minus 3 inch, right. That is the error we will get. So, the first part of the question is calculate the error in an 11 inch measurement when ambient temperature is 100 degree Fahrenheit. So, we will have error, that is 3.08 into 10 power minus 3 inch. Now, second question is, should the person using this scale be concerned with this error? If he or she is concerned, then why, and if they are not concerned with this measurement, then also why they are not concerned. Precision. Now, the precision of the instrument is least count by 2, that is 0.01 by 2, that is we can write 5.0 into 10 power minus 3 inch. So, what we can see, the precision of the instrument is 5 into 10 power minus 3, where error is 3.08 into 10 power minus 3. That means, if we use this scale to measure 11 inch in a condition where ambient temperature is 100 degree Fahrenheit, then the person who will be using this scale should not be concerned about the error, because least count. So, we should not, I am writing, we should not be concerned about the error because error is, it is smaller than the precision of the scale. So, this is the first answer, and error, second answer, error is 3.08 into 10 power minus 3 inch. So, this is the second answer. So, the person who will be using this scale should not be concerned about the error, because precision of the error is smaller than the precision of the scale. So, to summarize today's discussion, we have discussed about, we have taken one example to see, rather to follow the steps using the Chavinet's criterion for rejecting data, and then we have discussed about the error propagation, and considering a single variable function we have worked out the we have analyzed the error propagation using statistical method, and then we have discussed that if the function is two variable function, the function is having two variables or several variables, then what will be the error and the standard deviation. Finally, we have worked out one example to calculate the error associated with the measurement or distance using a metal scale, and the problem which we have worked out is largely related to the fixed error, and we have seen that the error which is coming out with this measurement with this measurement, and finally we have discussed about the precision of the instrument, and we have seen that the error which we have calculated, which is less than the smaller than the precision, and that is why the person who will be using the scale in measuring that small distance should not be concerned about the error. So, with this I stop my discussion today, and we will continue our discussion in the next class. Thank you.